Again, what we're taking a look at is the location of our peaks or our signals, or you'll even call them, hear them be called as resonances. Either one works. Again, to the right is 0 parts per million. To the left is approximately 12 parts per million. You can set it up to be whatever you want, but most organic compounds are between 0 and 12. And remember, this side to the right is the shielded or the upfield portion. And then to the left is the deshielded or the downfield portion. And so as we previously said, these electrons shield the nuclei from this external magnetic field. And so the more electron density you have around this atom, the more shielding you have. And so naturally you might be asking what deshields? And the main thing that's going to happen is the inductive effect. Right, if you're next to some kind of electronegative atom, let's take chloropropane. For example, we have these two hydrogens right here, and then chlorine is very electronegative, which means it's pulling those electrons away from this carbon, and thus the hydrogens on this carbon. And then we have these 3 protons over here. And then if we think about which one is going to be further to the left, it's going to be these 2 protons, right? These are going to be further to the left because they're closer to this more electronegative element. And so they're getting their electrons stolen from them and they're getting deshielded, right? And so that's what you can see on this NMR, right? We can think about it ourselves and match it up. So we have 2 H's here. And then we have 3 H's here. And what we would expect is to have a peak to the left that corresponds to those 2 H's. And then a more shielded peak or a more upfield peak that corresponds to our 3 purple H's. And that's exactly what this picture shows, right? So here are those 2 H's right next to the chlorine. You can see they're further to the left, while these 3 further away from the chlorine are further to the right. Don't worry about the splitting on the peak, just worry about the location for right now. Another common thing that's going to deshield is what's known as the anisotropic effect. We're not going to go into detail about the why behind this. All we need to know is that aromatic compounds and all pi bonds will experience this. An aromatic compound for now we're just going to refer to as benzene. So we'll later on know much more about aromatic compounds, but for right now we're just going to stick with benzene. And then of course pi bonds or any double or triple bonds. I have this kind of picture right here. You can watch it, or you can look at it and try to kind of decipher what's going on here, or you can do some Googling. It doesn't matter. So over here to the left, we have the NMR of benzene. And so in benzene, all of the protons are exactly the same. And as you can see, this proton is quite deshielded, having a ppm of something like 6.5, right? So being next to an electronegative atom or next to a pi bond or an aromatic compound, benzene will cause you to be deshielded, right? And so chemical shift is determined by the local environment. So just some useful things to know. Say like we have propane right here. We have 2 types of H's. We have the H over here and then the H over here. They're both going to be relatively shielded. They're both alkyl, and so they'll show up somewhere between 0 and 1.7 parts per million. The one on the right here will be more shielded, or more towards the right, or a lower chemical shift, whichever way you want to see it, where this one will be more deshielded, more downfield, more to the left. larger chemical shift, that kind of thing, right? Due to these other carbons that are around it. Some other useful things to know are allylic hydrogen, so not in the pi bond, but next to a pi bond, will be approximately 2 ppm, while vinylic are around 4.5 to 6.5. Alkynyl will be around approximately 2.5. If the hydrogen is on a carbon that has an alkyl halide on it, that'll be somewhere between 2 and 4. Aromatic compounds, or in our case just benzene, will be somewhere between 6.5 and 8. And finally, one more, the aldehyde peak will be around 10. I lied. One more. And then the carboxylic acid hydrogen will be around 12. Right. So again, we're talking about proton NMR, so we're talking about these protons that exist here. And you can look up all kinds of charts for this, right? So on the left is just like a little diagram that shows you the same thing that we just covered up there. And then on the right is kind of the same thing as this diagram on the left, just in a table format instead. So I don't expect you guys to memorize any of these things, but you want to have a table handy. That way you can identify some things, right? If you see a peak somewhere between 10 and 12, chances are you have a carboxylic acid. If you see something around 10, you probably have an aldehyde. If you see peaks from about 6.5 to 8, you probably have an aromatic compound. If you see something right between like 4.5 and like 6.5, you probably have some kind of alkenes. OHs and NHs kind of have a broad range. If you see something very low shift, that'll probably be an alkyl chain, that kind of thing. So just some useful clues you can get from these NMR spectra.